This also brings me now to today's real topic, and Professor Karin Jacobs, who published a few years ago a very highly cited article in the Beilstein Journal of Nanotechnology, which is also about adhesion. And I want to give you a short introduction. So Karin Jacobs studied physics at the University of Konstanz in the south of Germany, where she received her PhD in 1997. She had a postdoctoral stay at the MPI for colloids and interfaces near Berlin and became a research assistant at the Ulm University in 1999. And then she did a short excursion away from academics and became a group leader at Bayer Polymers for 2 years until she came back from industry into academia and became a professor at Saarland University in 2003. She has had several research stays internationally in Israel at the Weizmann Institute of Science or in Australia at the Ian Walk Research Institute. And beside this, she's a member and fellow of several well-renowned important research institutes and academies in Germany. And maybe most notably, she's also a vice president for the DFG, the German Research Foundation, where she is responsible for helping young researchers in their early career stages. Besides helping people who are trying to become a professor, she's also very active in the field of promoting young people for their interest in science, which can reach from the kindergarten up to the higher levels of schools here. And I think I can tell you a lot about her research, but I think this is best done by herself. And with this, I want to give the field to you. Thank you very much for giving this talk today, and I'm looking forward to it.
Thank you very much, Max. Just two things I would like to add is that due to my engagement with Bayer at Leverkusen, I'm very happy that the soccer team, Bayer is now German soccer master for this year and breaking down the long tradition of Bayern München for being the only giant soccer team in Germany. So second thing is indeed have a look at the Beilstein publication series. It's a very nice process, and I promise I will do some publications with you once again. And because the journal that you mentioned is really nicely cited, so the Beilstein Journal of Nanotechnology is highly visible. And it was a great experience to publish with you. So thank you so much for joining the talk and having me as a speaker today. Yeah. So why do things stick? This is a question that also my little son poses, who's now in the elementary school. And here's my team at Saarland University in Saarbrücken. We are closer to Paris than to our capital in Berlin. However, we are a middle-sized university in Germany and are hosting a huge collaborative research center joining forces between biology, medical sciences, and physics.
I'm sorry, so I think you have to share your screen again. Because
I have to share my screen. Okay, let me see. Where is it? I have to share my screen. No?
Yeah, that looks good. Thank you.
Yeah. So
yeah.
Am I in presentation mode? Yes.
Yes.
So Saarland University Saarbrücken, that's my team here, and we also here interdisciplinary. So we have also people from background biophysics and biology. And myself, I come from surface science, and now this should be going on now. Yes. Functional materials, really very controlled surfaces. Then I went on with my PhD to do microfluidics and look at the stability of coatings. And this brought me to Bayer Leverkusen looking for polymer wetting properties. This, for instance, is a base coat, a white base coat lying on a Ferrari hull tin. And as you can see here, this is not what you want. Even if the red color comes on top, you will have a rusty Ferrari if this is not managed here. And from microfluidics, I went on because we gained a lot of knowledge how fluid, liquid, soft materials interact with hard materials with surfaces, and this very natural made the connection to biological systems. So to look at bioadhesion, because the physics behind is identical. Now, what I'm telling you today is concerning bioadhesion. Our aim is to understand bioadhesion, and if everything goes nicely, also give design rules, how things should be designed, implants or catheters or anything that the needs are best served. So for example, can we understand and prevent caries? So caries is these nice little holes here in our teeth, and responsible are these two guys here, Streptococcus mutans and Streptococcus oralis, who nearly everybody of us carries in the mouth. So somehow we need to, we have adhesive forces because these bacteria stick to our teeth. And where they stick, they make their metabolism, they eat sugar and put out lactic acid, and the lactic acid dissolves the tooth material. But they're only happy and they're only doing the metabolism if they are settled. So this means they're really looking for places where they can nicely sit down and then grow. So they need attractive forces. What could these attractive forces be? So there can be forces due to unspecific interactions, like screened electrostatic interactions, because a bacterium is charged, the substratum can be charged, especially if it's in a polyelectrolyte solution, like in our mouth. We can have van der Waals interaction, so it is just an induced dipole moment that induces interactions to other dipoles. Or we can have short range interactions, so-called hydrophobic interaction, or interactions that are highly repulsive, like the Born repulsive forces that make sure that not two electrons to have the same quantum numbers, and therefore objects cannot interfere with each other. So, and there is steric hindrance that also leads to repulsion. Steric hindrance is, for instance, if we have bacteria that have long legs, like so-called pili, and if they encounter a surface, they prevent the bacterium from really going in hard contact with the surface. It's like a dish of spaghetti where one spaghetti cannot go through another spaghetti. The same phenomenon of steric hindrance takes place if we have these long chains coming from the surface, if we have a brush or hairy surface, something like this, or in this, how it is sketched here, if we have both. So what are we looking at? We can look at proteins, like for instance in our mouth there's the protein lysozyme. We can look at bacteria. So from the physics point of view, these are small objects like Staphylococcus aureus, Staphylococcus carnosus, or the two mouth bacteria. And as substrates, we can use anything that is somehow stable in buffer solutions: steel, titanium, silicon, gold, silver, whatsoever. But next to the unspecific interactions that we can find everywhere, there can also be specific interactions, so-called ligand-receptor interaction, wherever the receptor is, or we have ligand-mediated interaction. But these are specific to the object, specific to the substrate. So the only specific interaction we will have in our systems, because we cannot exclude it, are sulfur or hydrogen bridges. So, and we do a lot of effort to distinguish specific from unspecific, but also to distinguish, what is now really responsible for the sticking of bacteria or for the sticking of proteins. I won't be talking too much about proteins in that talk. So that we can say, is it due to short-range interactions or is it due to van der Waals that these objects stick? So for the remainder of the talk, we don't look too closely into these specific interactions. Now, how do we determine adhesion forces? Our main technique is atomic force microscopy, AFM, force spectroscopy. So we can scan the surface, for instance, to determine the roughness of this of a substrate. But to measure the adhesion forces, we use the cantilever as a force sensor. So here's the AFM cantilever, and it doesn't have a sharp tip. Rather, it's a tipless cantilever, and we attach one single bacterium to the cantilever. That's how the situation looks like in the scanning electron microscope. And you see this guy has a diameter of around 1 micrometer. Now, this is indeed a living bacterium. We learned how to stain it. And if this dye shows a green color, it is still alive. And even after 100, even after 500 force distance curve, this bacterium, this single bacterium, is still alive. We can put it into a nutrient and then it will divide, and so it seems to be happy. We can intentionally kill it by just dipping it into ethanol, and then the other dye, the red dye, is visible. So that's really simple, even for physicists, to see who's alive and who's dead. So we know we can do a lot of experiments with one and the same bacterium. So we can do 20 measurements on one substrate, then do 20 on substrate B, then go back to substrate A, B, and so on, so that we also can see if some deterioration or something happens to the system. Now, what can we measure? That's how we probe. We press on the surface, hold a bit, and de-adhere again. So we do an approach. Then shortly above the 0 distance of the substrate, we often record a jump to contact, not on every surface, but I will show on which surfaces we see it. Then we really press it so that we come into the positive force regime. This is the so-called force trigger. So we always have a force of, let's say, 100 nanonewton, wait for some milliseconds, a second or 5 seconds, see if this makes a difference, and then de-adhere. And for the de-adhesion, you see there's a hysteresis between the blue and the red curve. And this is because there is some adhesive force between the bacterium and the surface. So the minimum here of the red curve gives us the adhesion force. Sometimes this is a bit curvy here, and then it does make more sense to give the adhesion energy. If we do the integral over the red curve, we can see how far we have to retract the cantilever until we really lose contact. And there are some other things. I don't go into detail here. Now, how does the making of the contact work? And this is what we published here in Beilstein in 2014. And that is a really, really crude, rough model of how bacterial adhesion works. This should be the cell wall. This is not hard like steel, but quite rigid. And these little springs here should represent the proteins that are anchored on the cell wall. And if a bacterium comes into contact, it's not the cell wall itself that makes the contact, but it's the proteins. So now I just do it again. The proteins wobble on the surface due to the ambient temperature. So it's and then you see the longest, the wobbly ones that try to if they find a good sticking point, they make the first contact. But here you see we haven't got yet reached the maximum number of proteins attached. Now we need to enhance the force trigger, but still the adhesion force is larger than before. And now we really make sure that we get the most springs, the most proteins in contact, and then we get the maximum adhesion force. So this is how we do the experiments first, and then we see that we have stable experimental condition. Now let's test a very, very physical point of view experiment now. We take a silicon wafer. One has a natural silicon dioxide skin on the surface, And if you take a wafer out of the package from the manufacturer, then it usually has 1 to 2 nanometer silicon dioxide on the surface. If we intentionally make this dioxide larger, we don't change the surface chemistry. It is still SiO2, silicon dioxide. We can probe this by photoelectron spectroscopy. However, this silicon dioxide is a purely dielectric material lying on a semiconductor. Here, the dielectric material is much smaller. So the intention is to see if the depth in the subsurface of the material does play any role in stickiness, in the adhesion force. Then we have a wafer that is a pair of wafer that is identical to this one, but it has a coverage of a self-assembled monolayer, a silane layer. So this adds to this dielectric layer. It has nearly the same optical properties than the silicon dioxide, but the surface chemistry is different because it has a CH3 group pointing outwards and makes the surface highly hydrophobic. So here we have a water contact angle of about, well, less than 5 degrees. So it's really wettable by water. And here we have 160 degrees, so nearly like a pearl on the surface. Now let's see. If we do fast distance curve, and the occurrence of a certain adhesion force, here given in nanonewton, is for the thick silicon dioxide layer, here 0.3 nanonewton with an error bar of 0.01. This is what is given here in brackets. And if we are doing the same measurements on the thin silicon dioxide layer, then we gain about a factor of 2 larger adhesion force. And this can be understood because the silicon as a semiconductor is more polarizable than the dielectric layer here. So if it is lying on the thick silicon dioxide layer, the van der Waals forces are reduced. I can get into details if you're asking me later. So now the question is, what happens actually? These two have the same surface chemistry, so it's really a matter of the subsurface that makes a factor of 2 difference. If people don't discern these 2 types of surfaces, they will have a big Gaussian heap here, right? Depending on how their surface looks like. Now, what if we now make the surface hydrophobic just by this one monolayer of silane molecules? Now you see, we again see a difference. But the difference is not as high as before, but this is because we do have a 3.7 nanometer thick dielectric layer because we compare the 2 nanometers silicon dioxide with the 1.7 nanometer of the silane, well, 2 nanometers. So theoretically, we can nicely understand that. So van der Waals forces, this is a signature that van der Waals forces are important for adhesion. However, if you compare the red and the blue results here, you see that the adhesion force here is in the range between 0.2 and 1 nanometer, and here it's between 1 and nearly 10 nanometers. This means van der Waals interactions are indeed important, yet the short-range forces have a larger impact. So it makes a difference if there's a silicon dioxide on the surface to the bacterium, or if there is a CH3 end group in contact with the bacterium or with the bacterial proteins. Yeah, so what? In our mouth, we don't have silicon and we don't have any silane SAM. So, actually, there should be, okay, it comes later. I would like to show you what the situation in our mouth is, but obviously I first concentrate on the form of the force distance curve. How do the force distance curve look like? So, on the hydrophilic surface, the both clean silicon wafers where we have these weak adhesion forces, we see the approach. We see no jump to contact. The light blue is the approach curve, and the dark blue is the retract curve. And you see one and the same bacterium, four force distance curves of one of the same bacterium at nearly the same spot. I say nearly because I just at the moment don't know if this is from a series of little jumps of 1 nanometer. I think this is on really one single spot. We can do both. And for this situation, it doesn't matter. So you see it's a bit of a variance here, not much, but the variance. The retract curve are really spiky. And the approach, at the approach curve, we don't have a jump to contact. So this is how it looks like, the frequency or the how often we face the adhesion. You see it in between 0 and 1 nanonewton. So for the hydrophobic surfaces, note the distance in scale here. This is 10 nanonewton. We face strong adhesion. We have very smooth curves, and we have a nice jump to contact. And the jump to contact begins at about 15 nanometers above the surface. 50 nanometers. So that is out of the reach of intermolecular forces, because intermolecular forces, screened electrostatic forces, they are nearly zero if you are, let's say, 3 times the Debye length into the system from the surface, and this is about 10 nanometers. Okay, so we're here at 50 nanometers. So it was from the beginning quite clear that this cannot be the signature of an attractive force between the bacterium and the surface. Rather, and we could show that by varying the type of proteins on the surface. This is a matter of how long are the longest molecules that are wobbling away from the bacteria surface. And we can say, when they are a little bit stretched at ambient temperatures, they can be as long as 50 nanometers. That's the message from the snap to contact part of these curves. Now here we see the frequency of the adhesion force. This is Staphylococcus carnosus, okay? So this is a guy that really sticks heavily, one of the really best stickers we have. And you see they can have adhesion forces up to 60 nanonewton per bacterium. This is a lot. And this means if you have a catheter that should go into your vein and you clean it, you need to have really high forces to get it away, or you really have to dip it in alcohol or somehow get it away. And this Staphylococcus aureus, that is causing many millions of infections every day. So it's a really nasty guy. So the hypothesis here for the hydrophilic surfaces, for the clean wafers, is that only few molecules of S. aureus are involved in the adhesion process. And here, because we have those smooth curves, many molecules are involved, but we don't know how many, and we don't know how strong the interaction is at the hydrophobic surfaces. Now, you see here, we seem to have 2 Gaussian distributions. This is a very typical signature from the S. aureus. Before I showed you Staph carnosus, it doesn't show these two contact scenarios as we hypothesize is. We will see later how we might be able to explain that. So, but we first need a model of bacterial adhesion to understand these post-distance curves. And I showed you already a suitable model, a sphere decorated with elastic springs, but a protein is not an elastic spring, is a worm-like chain, right? So if you stretch it, it's not a linear stretch with force. The more you stretch a macromolecule, the more force you need. And therefore, you need to introduce the worm-like chain model. Our collaborators from the theoretical department, and here I would like to name my colleague Ludger Santen, they showed that they cannot reproduce our curves without assuming a distribution of spring constants. So this means very likely that not a single type of protein is involved in the adhesion process. Rather, we need a collection of different molecules. They assumed the short-range contact potential to mimic the hydrophilic-hydrophobic interactions. And here is the experiment, one of those curve pairs I showed you before. And here's the Monte Carlo simulation. And you see here, if you compare the blue curves between experiment and simulation, you see this typical signature here, these curves. And this is the signature of a worm-like chain. You need more force the more you extend the molecule. So a worm-like chain signature, and in the simulations, they had to assume 22 proteins per micrometer with an attractive potential of 54 kBT. On the hydrophobic surface, however, we have these smooth curves, and they assume 32,000 proteins with only 18 kBT. So we think that in this case, we speak about single proteins that form hydrogen bridges with the substrate. And another point in this direction is that if we wait in the experiment longer, we get more of these few events. It goes into saturation after 5 seconds, so 5, 6, 7 seconds. If we wait 10 seconds, we don't get more. And here we think of that weak hydrophobic interactions make the attractive force. This is really weak, but we do have many proteins. So we have 32,000 proteins per square micron. And if we break it down to the contact area, which I will show you in a minute how we determined that one, for the hydrophilic surface, we record 4 to 8 molecules. We can really count them, 1, 2, 3, 4 here. And for the hydrophobic surface, we think of 5,000 to 6,000 molecules per contact. Here it is, prevention of caries. This is now done with a group of Staphylococcus oralis, not with a single one, to get a bit more statistics. But we know how many it were, so because we can see them with an optical microscope. And we pressed on and lift off this group of mouth bacteria onto tooth-like material. We made ourselves hydroxyapatite pellets. This is an extra publication where we show that they're really similar to the real tooth material. So we took the artificial tooth material untreated, and then we used fluoridated mouthwash to treat it, like we may using it for our daily mouth routine. And we found out that the fluorine is present within the first 6 nanometer of the surface. So we compare these two pellets. And first I need to explain what actually why fluoridation really works for the prevention of caries, because the fluor atoms, the fluor ions, go into the hydroxyapatite material and replace the hydrogen for fluorapatite you get later on the surface, and up to 6 to 10 nanometers into the surface. Now, fluorapatite is less affected by the lactic acid that is produced by the bacteria. So fluoridation causes a reduction of the solubility in lactic acid. So they can produce lactic acid, but on the place where they sit, our tooth material is no more dissolved. Now we can say, let's have a look at the adhesion force in nanonewton for strep mutans, strep oralis, and for comparison, the staph carnosus from before. And you see untreated in blue and fluoridated in red. And we have a reduction of adhesion force by a factor of 2. 50% less adhesion force of bacteria, but this means that the probability of the bacteria to sit on our teeth is reduced. And second, it's much easier to remove them again from our teeth with the toothbrush. So there is a twofold explanation why fluoridation works. But the biggest counter argument is, these are not real teeth. So the distinction between the hydroxyapatite pellets and real teeth is that on real teeth we have 5% organic material in between the segments of the macrocrystals of the hub of the hydroxyapatite. That's the difference. So I would say from a physical point of view, we can explain 95% of what's going on our teeth. But there's 5% unknown, okay? So I'm not talking about real teeth, but from my point of view, I dare to transfer the results to real teeth. And real teeth have the problem that the fluoridation of the surface needs to be characterized before every experiment, because if we get teeth, usually from bovine, from cows, from the slaughterhouse, then you don't know how this cow was fed, and therefore we don't know if it was standing on a lawn where it got some fluoride to fluoridate the teeth from the very beginning, like you do with the babies, that you get fluorine tablets. And this is making the experiments very, very cumbersome. Before each experiment, you have to go to the photoelectron spectroscopy, right? But this is what we do now to really rule out any effect of the 5% organic material. All right, now the question is, which area is actually in contact of the bacterium? So we make use of the strong difference in adhesion force between the hydrophobic and the hydrophilic materials. So what we prepare is, we prepare an interface on a silicon wafer between a hydrophobic and a hydrophilic part. So as before, the hydrophobic part is made up by these monolayer of silanes. And here is only hydrophilic silicon. And here you see the interface region has a size of about 30 nanometers. Compared to the size of 1,000 nanometers of a bacterium, this is really small. This not really nicely determined part is very small. So what we do is we start here with force distance curves and then go along these pathways doing force distance curve, hundreds of force distance curve, until we end up in the hydrophilic silicon. And then we plot the adhesion force as a function of the distance between the hydrophobic and the hydrophilic silicon. Here it is, it's done with this Staph aureus. You see from the side the contact angle. Here is the interface between the hydrophobic and the hydrophilic layer. This is a water droplet, and as I said before, here the contact angle is about 112, 106, up to 116 degrees, and here it's nearly not measurable. Now we start on the hydrophobic part and record the adhesion force. Here's the entire curve, and the minimum gives us here the adhesion force, and this is plotted with this little star. And so we make our way. I don't show you all the distance, all the curves, because you wouldn't see anything. And you see, as we reach the hydrophilic part, we reach really only a factor of, well, a tenth of the starting point in the hydrophobic part. Now we have a little model, assuming that the contact area is round. This is very easy geometric model with some arc sine, arc cosine in between. And so as we go over the interface, the adhesive force decreases, and from the geometric model, we can get out the radius of the contact area. And you see, this is now for S. aureus, and we would say it's the radius of contact is between 150 and 320 nanometers. And now the question was, S. aureus has this strong adhesion. If we now compare it to S. carnosus, does S. carnosus have a smaller contact area? And the answer is no. it is in the very same range, yet it cannot be the contact area, it must be the species-specific chemical composition of the surface, of the bacteria surface. Or in other words, the type of proteins that are present on the bacteria surface. Now, if we just compare that with a hard glass bead of the same size, what actually happens? So remember, the diameter of the bacterium is roughly a micrometer, 1000 nanometer. And here is the contact area that I showed you, the radius between 150 and 320 nanometers. So here, the contact area is about 1/3 to 1/6 of the diameter of the bacterium. If you do the same measurements with a rigid sphere of 1 micron, we get as a contact area 1/20th of the diameter of a glass bead. So the bacteria are the master of making good contact for their small size. So the question is, how do they deal with roughness? Before, I just showed you very smooth surfaces. As smooth as you can get is a silicon. This is one of the smoothest surfaces you can get, maybe except for graphene or some other nanocrystal. And we can roughen it by hydrofluoric etching, HF etching. So we get roughened, so-called also black silicon, because then it's not mirror-like anymore. On the contrary, it's really black. And the question is now, does surface roughness influence bacterial adhesion? Is there a certain type of roughness that enhances or reduces adhesion? And can a spiky surface kill bacteria? So over this topic, I could give you a single talk. And the simple answer here is yes, surface roughness influences bacterial adhesion. A certain type of roughness can reduce bacterial adhesion, but it can also, another type of roughness can enhance adhesion. And indeed, a spiky surface can kill bacteria. Precondition is the spikes must be hydrophobic. And then the spikes go into the cell wall. It's like a harakiri of the bacterium. The bacterium really likes is attracted by the spiky surface, and there is then harakiri, so these spikes go into the cell wall, and the liquid that is inside the cell goes out, the so-called lysis, and then the bacterium is really dead. Now, which type of surface does really matter? You can imagine that if the surface provides a very nice roughness with curvatures in the range of the bacterial radius, then you have a really smooth cushion for the bacteria. If it's larger, the bacteria don't care. But if it's smaller, the question is, do the proteins reach the surface? So actually, you would think if you have a rough surface, the actual area you have in contact with air or with the saliva of the mouth is much larger as if it was smooth. So from that point of view, you would expect that you have a higher adhesion because you have more material the proteins can attach to. However, if the deep valleys are not accessible, you might reduce the accessible adhesion area for the bacterium. And this is what I will concentrate on. Here's the sketch of that. So the bacterium might not be able to reach deep crevices and stick to only here the mountains. This is what we measure. We have 4 types of rough silicon. So we etch longer and longer. So the roughest is the root mean square of 35 nanometer, starting with a smooth silicon wafer of only 0.1 nanometer. And here, that's just the normalized adhesion force, normalized to the smooth silicon wafer. And you see, these were 10 different bacteria that had been tested on all of the 4 surfaces. So this is the measurement of one cell on 4 different surfaces. The smooth one, the 7 nanometer, the 24, and the 35 nanometers. And we have sorted the 10 bacteria for the results of the adhesion force. So now let's take the mean value of all these 10, and then you see a small roughness doesn't change much. The error bar is a bit larger than for the complete smooth surface, but as soon as we go over the 10, 12 nanometers, we see that the adhesion decreases, and the roughest surface we were testing were the 35 nanometers. So adhesion force decreases with increasing roughness. Now, can we quantify that? And here are the original AFM scan. Each of it is one line on the respective wafer series, and you see that when it's very rough, indeed, the deepest valleys cannot be reached. This should be about to scale for the bacterium. So for proteins, that's where the contact is made from the bacterium. The accessible is the real surface area, and this decreases with increasing roughness. Yes, we can quantify it. Here you see a rough surface where we have the geometry of the tip deconvoluted. Now, if we look from 3D, we see that the surface is really rough, is really spiky. And now we would like to see, how far do these proteins reach into the surface. So we do a watershed and go maximum from the top to 50 nanometers down. Now, what area is left? And this is subsummarized here. White is the accessible area. Okay, this takes into account the size of the proteins. Now, we come from above and see how far do we reach with 50 nanometers. Suppose it's that, then this material is just lost for our bacterium. So here, let me see, here is the diagram. The real surface area is divided by the projected area, and this is 1 for the green smooth surface. Now, it should be larger the rougher you get. Therefore, the yellow one with 7 nanometer is exceeding it. But you see, it goes slowly here to this 100%. Now, for the rougher and rougher ones, we have to go deeper into the surface. And remember, 50 nanometer is about the arm length of our proteins. So for 50 nanometers here, we see about 0.35% of the projected area. For here we see 60%, and for all the others we should see 100%. Now let's see what we measure. Indeed, 0.4 for the roughest surface and 0.6 for the second roughest surface, and 100% for the smoother ones. And yeah, this is also a bit of a longer story, but you see that we can really correlate the accessible area with the measured adhesion force. So our hypothesis is okay. We can again change the tether length, and indeed then the result changes to lower distances from the top. Now, the morphology of the surface roughness is really important, and that's what we are up to now. We look at different types of roughness, some smooth surfaces with deep crevices, and just the opposite, smooth surfaces with some spikes, or anything in between. So, is adhesion homogeneous all over the cell wall? This is my last chapter, how to probe that. Therefore, we take a structured surface. We can then selectively cover it and see if there are certain parts of the surface that make an especially high contact on that part and not here. So is the force identical here, or do we have there another group of proteins that do not like the red coverage? Okay. Now, once again, what we do. We take our bacterial probe as before, but we have a sinusoidal surface structure. So for the specialist, it's a PDMS surface that had been prepared and stretched and then released, and then we get those surface ripples. So it's a hydrophobic surface that the Staphylococcus aureus really loves. Now, we do force distance measurements here, then move on, do it here, move on, do it on top, move on, and so on. So it's clear that on top, we expect a smaller contact area because of the non-matching curvature. Here, we expect a higher contact area. So we don't compare these two cases, but we know in the valleys, we should expect a higher adhesion force. But if we compare that part, that shoulder of the ripple, with that shoulder of the ripple, if the adhesion is homogeneous all over the bacterium, and the bacterium is firmly glued here, so it cannot move, then these two parts should be identical. Now, we need to do a lot of measurements, and you see here, you know, that's the wavelength of the ripples, and the amplitude of the ripples is now in the range of the bacterium. Now I plotted 4 periods of force distance curves. So this is one period, 1, 2, 3, and 4. And now you see this is the adhesion force as a function of the relative position of that ripple. 0 is in the middle, where we expect the lowest adhesion force. And indeed, in the valleys, we have the highest adhesion forces. But now look, here, obviously, this is somewhere there, we seem to have a high adhesion force for a certain distance. If we are here with our measurements, it's the same. Another period here is the same, and the period before it was also the same. So we can overlay these 4 measurement paths. And here you see the single. These are all together, there were around 20 cells that we were probing. And some of them were showing this signature of higher adhesion somewhere. By accident, it could obviously also happen on the peak, on the mountain of the structure, but very often somewhere on the side. But not always. There are a lot of cells that don't show any enhanced adhesion signature. So, but this can happen, right? So I just plotted here our imagination of, you know, a group of highly adhesive proteins. And if we do just the adhesive measurements where there's not such a group, we don't see it. Okay. Now, from the signature that I said, that the width here and the probability of how many of our 100 cells are seeing where we see such a signature of high adhesion, we can make a prediction or a geometrical visualization of how wide and how often we should have these parts, these sites of higher adhesion. And this is about that. Okay, here are the size of the patch, diameter about 250 nanometers, so the contact area that we used to expect. The number is between 3 to 6 over the bacteria surface, and the distribution is the widest possible distance. What is open is the nature of the involved proteins within the patch. We really have no idea, and we also don't know the nature of other patches. Oops. Yeah. So there should be. Okay, it's not. And I can just conclude with all what I've been saying to you. Stickiness can be quantitatively determined, even in systems that are not highly controlled, like on teeth, like in bacteria in buffer solution on even rough surfaces. Monte Carlo simulations with the group of Ludger Sanden, they are superb to interpret force distance curves. And for different surface energies, the number of tethering molecules differs strongly. We have a notion of the involved forces in some of the specific systems I've been showing you. There, it was hydrophobic interactions on the hydrophobic surfaces and hydrogen bridges on the hydrophilic surfaces. Altogether, I can say for the bacteria we were looking at, hydrophobic surfaces make a stronger contact than hydrophilic surfaces. So if you ask me if a door handle should be metal or plastic, as most plastics are hydrophobic, I would say go for the metal door handle. The contact area we have been able to probe. We could do a hypothesis about the type and the density of the cell wall molecules. And we know that it is more important than the actual contact area. And we found out that adhesion is non-homogeneous over the cell's surface. Roughness in the nanometer range is very important to quantitatively understand adhesion forces. And for some systems, we can say by inducing spiky surfaces, we can really prevent bacterial adhesion. Conclusion and outlook. Bacteria seem to be patchy colloids. And this was the sketch I expected before, because not only we don't expect that we only have a certain group of proteins forming the interactions, like the hydrophobic interactions. We expect also other types, like specialists for hydrogen bridges, specialists for fibronectin binding, and these colleagues have simulated that it could look like that we really have a patchy surface with functions that suit every need of a bacterial adhesion situation. So I would like to thank my team and to all collaborators. I like to thank the funding agency, and for sure, I like to thank you for your attention. And I'm happy to take your questions, either in person or by looking at the chat.
Yeah. So thank you very much for this very wonderful talk. Again, I see some questions in the question box. If you want directly talk to Professor Jacobs, then you can raise your hand. Aha, someone is raising their hand. Okay, let's start chronologically, or maybe start with a greeting. Thank you for a great talk, Karin. Best wishes from Berlin, from JPK Brucker, from Alexander Dulebo, who already. Okay, now let's get to the question. The first one is regarding the first part of your talk. Is von René Riedel, how do you manage to attach one single cell to the AFM?
Yeah, so for staph carnosus, it often is not really necessary to glue it. For gluing, we usually use either polylysine or dopamine. So this glue is attached to the cantilever. Where do I have a cantilever here? I have a cantilever. And then you have a petri dish. And because the bacteria are large enough, you just go fishing. So you look for a single bacterium on the petri dish, and then under the optical microscope, you go and attach with a cantilever on top of this single bacterium, press a little, take off, and then you have this little bacterium on the surface, like my little ball here. It's not as simple as I told you, but when you have a bit of skills, within a week you can learn it.
Okay. Perfect. Thanks. The next question is from Stefan M.D. Schiller, who's asking, how do you make sure that the interaction properties of the bacterium bound to the AFM tip when different surfaces are tested stays constant? Or in other words, how much does the bacterium tip changes from measurement to measurement?
Yeah, it's a very important question, and we were very concerned with it when we 10 years ago started with that. And as I said, it's amazing, but we can easily do 150 force distance curves. And it doesn't matter if we do it to hydrophilic or hydrophobic material. However, what we see is, for instance, with the Staph aureus, that after 500 force distance curve, and starts about 400 force distance curve, that the maximum adhesion force we gain is decreasing. And we think because Staph aureus attaches or adheres so strongly that we lose a few of the other molecules. So we never exceeded 400 force distance curve. Usually it's way enough to have 150 force distance curves. And these 150 force distance curves we can separate into 2 or 3 or 4. I showed you 4 samples typically is the maximum.
Okay, thank you. The next question is from Karin Schwibert. Is adhesion force influenced by the bacterial growth phase?
Yes, very likely it is. And we are always in phase, now you get me, in phase 2. We always in the exponential phase, right? This is the task of our biological collaborators. That we have comparable situations of the bacteria. Very, very important. Thank you for this question. I tend to forget to tell you this. Yeah.
Okay, we have someone raising his or her hand. I'm sorry. Raja Gopal Rayavarapu. I will. So you are muted. We should hear you now.
Yeah. Good evening.
Yeah.
Good evening.
Yeah, thanks, Professor Jacob, for your wonderful and inspiring talk. Actually, I don't know whether my question is relevant to this talk or not. We are working in the area of nanoparticle synthesis. So what usually happens is, like, whenever we synthesize the materials and store it in a polypropylene tube, they tend to stick to the surfaces.
To what? They stick to?
Polypropylene tubes, like Eppendorf tubes.
Yeah.
So we are working with gold and silver nanoparticles. Always we see this happening to the walls of the tube, and next day it becomes water. So I try to understand what is happening with the nanoparticle to the polypropylene tubes.
Okay. Of what are your nanoparticles? Gold and silver?
Yeah, gold and nanoparticles of size 20 nanometer in diameter. They are spherical nanoparticles.
Okay. Okay. Well, you have already van der Waals forces, so you don't need anything else but van der Waals forces. They are always present and they're always attractive, so they always will go to interfaces.
Okay, so are there any coatings that I can use so that I can prevent my sample from aggregation or sticking?
Well, the best is you would use the same material. That's my guess.
Okay.
So gold or silver, coat it.
Okay, so to coat, I mean, then it becomes expensive. Okay, but thanks for your advice. I'll try to do. Thank you very much. Thanks.
You're welcome. Or make it hydrophilic somehow if you can.
Okay. Sure, Professor Jacobs. Thanks.
Okay, maybe we have time for 2 more questions. At the moment, they keep coming in. So, okay, Horacio Andres Vargas Guzman, I'm sorry if I pronounced the name wrong, is raising his hand, and he is now unmuted. He has to unmute himself.
Hello?
Yeah,
Hi.
I can hear you.
Okay, hi. So thank you for the nice talk. It's really amazing what you can do with an AFM. And I have a couple of questions, but to make it short, do you think this regarding this hypothesis of the patchy colloids with different regions? According to your experiments, do you think they are symmetric somehow?
Well, my gut feeling says symmetry is not needed there.
Okay.
I don't know. I don't think it brings any advantage for nature to have symmetry in that system. I think the highest order you can have here is that the patches have the widest distance possible on that round surface. I think that's enough. And if we say we have 3 to 6 patches and they have the widest possible distance, this is some kind. It's not a strict symmetry, but it's definitely a design rule.
I see. And just a short curiosity regarding the surfaces, because I mean, purely hydrophilic might be difficult to obtain in experiments. I don't know, but Have you measured the contact angle?
Yes, yeah, that's what we always do. For the now it depends on what surface you are asking for. I told you the contact angle of the silicon and the silanized silicon wafer, and
Okay.
yes, so we do that also for the implants. We do it for the catheters and so on.
So,
Yeah.
so contamination is not really a big problem, right? Or
not if we are measuring in clean buffer solution. But what I can tell you, there is no direct correlation between the contact angle and the adhesion, because the contact angle is a macroscopic description of a wetting situation, and the adhesion of bacteria and proteins is nanoscopic. Okay, it's a point-like interaction, and therefore the wetting properties do not directly correlate with adhesion. It can also contradict to each other. So it is good to know what you have for knowing or for determining the reproducibility of your preparation process of the different substrates. But it doesn't give any prediction of the adhesiveness of a biological system.
okay, perfect. Thank you very much.
You're welcome.
Okay, we have one last question from Brandon McClemon. Have you looked into how bacterial adhesion is mediated by biofilms, e.g. mucins on the tongue modify the hydrophobicity and increase the compliance?
Absolutely right. You're just describing our present measurements for sure. I mean, you know, physicists look for clean surfaces, look for clean buffer solutions. It's a nightmare if you go to the real mouth situation, okay? So, and the mouth situation is that we do have saliva. And in saliva, there are 400 different proteins. So we first thought, okay, let's have a look. If, you know, is adhesion different if we have a few proteins from saliva present? So we started with lysozyme, and indeed it is different. Interestingly, the Staph carnosus that lives on our skin is not really nicely concerned by the presence of lysozyme. It adheres the same. It doesn't adhere too much anyway, so it doesn't feel a difference if the surface is covered with lysozyme. Whereas the mouth bacteria, they are more sticky if there are saliva proteins present, like lysozyme. So indeed, this is a wide field and a vast combination of things you can test, but indeed, it makes a big difference. Yes. Thank you for the question. That was very important.
Okay. Yeah, thank you very much again for giving this talk. Was really wonderful and really interesting. And with this, I would like to close today's webinar. Thank you all for joining in. We would be happy to see you again at another webinar or at some other of our projects somehow. And with this, I wish you a nice day. And we can meet for like